Okay, here we go with second part of lesson 1.4. Still looking at continuity. Pretty much the focus on these ones is going to be these hybrid functions, also known as piecewise functions, where you're really given two separate graphs. Like this would be a line, this would be a parabola, but we are drawing those graphs on the same grid, and we are limiting their domains to what you see here. So for this guy, if I were to just draw the line of negative 2x, right, that would go on forever, but they want us to limit that graph to only this domain here, so only x's that are less than or equal to 2. For this guy, we have a parabola that would also be infinite domain, but they want us to limit this graph only to where x is greater than 2. So we have kind of a split going on here. So the first line, the first graph, the linear graph, only goes to the left of 2, and the parabola only goes to the right of 2. And we are basically checking to see, is this a continuous graph? In other words, does this line meet this parabola at x equals 2? Is it a continuous graph, or is there a break in the graph where x equals 2? So a couple ways we're going to look at this here. I'm going to show you the graph in a second, just to kind of validate the answer, but most of these things we'll be doing kind of without a calculator. So first thing we're checking for is, are the graphs continuous themselves within the domain that they're given? And of course these would. A linear graph is continuous from negative infinity to positive infinity. So of course it's going to be continuous to the left of 2. A parabola is also continuous from negative infinity to positive infinity. So he would have to be continuous for everything greater than 2. So good to go on those. We can use direct substitution as long as our graphs are continuous. There's no holes or asymptotes or anything like that that would limit these graphs. So we'll use direct substitution. So we're going to start out with the linear function, this guy here. So if we were going to look for the limit of f of x as we approach 2 from the left, which would apply to this domain right here. So we're taking a look at this graph. So we're going to do a little direct substitution and plug in 2 for this x. And we're going to get a y value at negative 4. So the limit of f of x as we approach 2 from the left would be negative 4. But what about as we approach 2 from the right? If we approach 2 from the right, well, now we're into this domain. And so we have to do our direct substitution into this function to see what we get. And in this case, we come out with a y value at negative 3. So just as we've talked about before, and this is what they're asking for if they say discuss your continuity, is if I am hitting different limits as I approach 2 from the left and as I approach 2 from the right, then we know this graph is not continuous, where x equals 2. So there must be a break in the graph or some kind of something that would show that this graph does not connect to this graph at the point where x equals 2. Right, because they have two different y coordinates as we approach 2 from the. I graphed these just so I could show you what this would look like. So this was the blue one is the line. So this would be the line of negative 2x. So I just started at 0. I went down to over 1. So this would be my line. But I limited that graph to only to where x is less than or equal to 2. And so that's where you get this guy from. This would be the parabola for x is greater than 2. Right? Obviously, we know this parabola would take a full curve like this, but they give us a domain that x is greater than 2. Right? So this is all we get to see of that parabola. Well, you can see right here where x equals 2, there's a break in the graph. Right? They don't connect to each other, so it's not a continuous function. So graphically, it's super easy to see it. But if we don't have the graph to work with, then this is kind of the process that we would take to get us there. So moving on down, this is going to be really the same idea. It's just a more complicated example. You'll have to pardon my work. Obviously, when I first wrote these notes out, I was not intending to do this on just video. This would have been what we would have gone through in class. So I'm going to explain things as best as I can, though, as we go through. So here we go. So stay with me on this one. So when we are testing for continuity of f of x, again, what we are trying to figure out is this graph connected to this graph according to this domain? So we need to take a look at this function according to this domain and y equals 2 in this domain. So I'm going to start out with just the upper function that you see right here, the cosecant of pi x over 6. Way back in your absolute value days in Algebra 1, when you first learned about absolute values, and this actually takes us back to Chapter 1 of this year, going back to doing these. If you remember, when you solve an absolute value inequality, there's always two setups that we use. We always say the original, x minus 3 is less than or equal to 2. So that's the first setup. But then we also have to test for the other set of solutions in an absolute value, where we would flip it and we would say x minus 3 is greater than or equal to negative 2. So we flip the sign, we throw in the negative, and these create our two possible solution sets. Because remember, with absolute values, it's just your distance from 0. So you can travel to the left or you could travel to the right. And so we have to look at both possible cases. If we solve each one, this is our domain that we get. We get x's that are less than or equal to 5 but greater than or equal to 1. So in other words, we are getting this graph from 1 to 5 is what that's telling us. So if we were to graph a cosecant of pi x over 6 is from 1 to 5, so we're only going to see this portion of the graph, then here's what we would see. So we haven't graphed cosecant graphs for a while, so I'm going to remind you of our little process for doing that. Remember, for a cosecant graph, cosecant is just the inverse of sine. So really what you're doing on this is you're graphing the sine of pi x over 6, which would be this red graph, right? And then since we're looking for the inverse function, we throw in the asymptotes at the zeros. So I have a 0 there, I have a 0 there, and I have a 0 there. So at the zeros is where the asymptotes go, and then we do the inverse function as a reflection within those asymptotes. So I have one reflection right here from 0 to 6. This would be the other piece of that. But remember, for us, we're only looking at this function from 1 to 5. So if you look, that fits within this little area of the graph. And in that area of the graph from 1 to 5, this is a continuous function from 1 to 5. So that's what we got for this first one. This was our little process for graphing our sine graphs. If you remember, you take your our b value, which is pi over 6, and we did 2 pi over b in order to get the period of the graph. So that's why I went from 0 to 12 would be one full sine graph. And then if you take your period and divide it by 4, that tells you what to count by. So that's why I'm counting by 3s, 3, 6, 9, 12, and that's what creates our one full period of that sine graph. So anyway, so our first function, the cosecant graph, is continuous along its domain. It's not continuous from negative infinity to positive infinity, but that's not what they gave us. They gave us a limited domain from 1 to 5, and so it is continuous from 1 to 5. And so that's one of the first things we have to check, and now we have to do the same thing for the second graph. So that was for the first one. The second one is simple. It's just y equals 2. That's all it is. And so, again, we're not going to see this as y equals 2 as it goes on forever. We are limiting that graph to this domain. So if I did the same solving process on this that I did over here, I'm going to see what my domain is. So what makes this one tough is they're not just directly telling you what the domain is like they did on top. All right, this was super simple. They just told us what the domain was. This one, they're like making us work for it. So little extra fun that goes along with this. So we're going to take x minus 3 is greater than 2 as our first scenario. But then we got to flip it, and we got to say x minus 3 is less than negative 2. Right? Putting in that negative causes your inequality to flip. So these are the two possible cases. All right, so we're now looking at where x is less than 1 or greater than 5 for this one. So these are like the two lines that go like away from each other like this. All right, less than 1 or greater than 5. We already know that this graph is continuous everywhere. So y equals 2 is just a line that would go on forever left and right. So of course it's continuous left of 1 and to the right of 5. This one we weren't sure about. The cosecant function is not continuous everywhere. So we had to sort of check this one to see, is it continuous within this domain that we were given. And we saw right here that it is continuous from 1 to 5. So that was something we had to check to see if that was true. But anyway, going on to the next part of this. So we sort of tackled the first question. So this was like part A. Are both functions continuous within their given domains? And so that's what we just figured out. So yes, they both are continuous. Now we can do direct substitution. And the goal is to try to figure out do these graphs connect within these domain values? So obviously we're going to be looking at the 1s and the 5s, right? To see, do they connect at 1 and do they connect at 5? To see if this is one big continuous graph that we're getting out of this. So I'm going to look over here. So if you look at our cosecant function, so I'm going to start with the 1s. So I got to say, sorry, I'm trying to get all this on the screen for you. So I need to look at my 1s, and we're going to say, okay, let's approach 1 from the right, let's approach 1 from the left, and see, do we get the same value? If we approach 1 from the right, well, that would fall under the domain of our cosecant graph because of this statement right here. So that makes it our cosecant graph. So if I plug direct substitution of 1 into my cosecant function, I get the cosecant of pi over 6, which is 2. So the limit of f of x as we approach 1 from the right is 2. The limit as we approach 1 from the left is also 2, because as I approach 1 from the left, now I'm into this domain, which means I am plugging into this function, which is always 2. So he's like an automatic 2 on this one. So yes, they connect. So for these two graphs, where x equals 1, they share a common y-coordinate of 2. So at the point 1, 2, our two functions meet each other. And that's what you're seeing right here. So at 1, 2, that's where they meet. So now we got to check at the 5s and see if they connect. So if we were to approach 5 from the right, that falls under this domain right here, which is always 2. So we get that answer real easy. As we approach 5 from the left, now we are under this domain, which means I got to plug it into this function, right? This guy right here. So if we put our 5 into that, it's going to look like this. And the cosecant of 5 pi over 6 is 2. So again, these guys do share a connection. They have a common y-coordinate where x equals 5, which is also at 2. And so we would see by all of this that, yes, this is one big continuous function. This is what it would look like if we were to graph it, right? There is no break in the graph. There's no hole in the graph. It goes left forever. And as soon as it runs into the cosecant graph, it connects right there. Here's the cosecant graph. And then where the cosecant graph ends at 5, it immediately connects back to y equals 2, which would then go on forever. So as you put these two functions together within this given domain that they gave us, it does create one big continuous function for those guys. So here's kind of what it all looks like put together. And so, yeah, pretty lengthy process on that. But again, the steps I was going through just take you back to these couple steps that you would go through on this one. All right, let me jump to the final portion of this here. Got to take a peek at these last two real quick. So this one is just a little spin on the question of what would this a value need to be in order to make this one big continuous function so that they would be connected where x equals 0, right? Because this one basically stops at 0 and this one picks up where the previous one left off at 0. So if we look at these two guys, let me go down to here. So since their connection here is at 0, we're going to say what would be the limit of g of x as we approach 0 from the left and from the right. if we approach 0 from the left, according to this, that would point us to this inner function right here. So I got my 4 sine x over x. Well, if we approach 0 from the left, remember you can't do direct substitution on this because of if I try to put 0 in for that x, we have an undefined point. However, 2 lessons ago, in lesson 1.3 part 3, we saw that the sine of x over x is 1. And so we can always insert that in for that guy. And so that gives us an automatic limit at 4 as we approach 0 from the left. On the right side, here's where we can kind of solve for a. So if I have this function, so for anything as bigger than 0, as we approach 0 from the right, we get to do direct substitution on this one because there's no issue by plugging in a 0 into a linear function like this. So as we plug in 0 for x on this one, again, we know the result must be 4 since this one was 4. In order for this g of x to be continuous, this limit and this limit must be equal. So we can put a 4 in for that one, and that gives us a nice easy equation to solve for a. So that gives us our a value. All right, last one here I got to show you with a compound function. So we're plugging g of x into f of x in order to create h of x. So here is our function for f of x. Here is our g of x. And so with this composite function, we are putting g of x into the f function. So I am taking this x minus 1, and I am putting it right there in for x. And that creates this look. So when they say discuss the continuity, what they're really saying is where is this graph continuous or where is it discontinuous? So for this one, the one thing we would really have to look at is really the domain of this. As you look at the setup that we have, we know that the denominator cannot equal 0, and we know we can't take the square root of a negative. So as I take my x minus 1, I know this x minus 1 must be greater than 0 because it's under a square root. I can't say greater than or equal to 0 because it's a denominator. So if it's on bottom of a fraction, I have to say that it's greater than 0 instead of greater than or equal to 0. Right? It can't equal 0 if it's on bottom. So solving that little equation tells us x can be anything bigger than 1, which means this function is continuous from 1 to infinity. So this has a lot to do with just kind of understanding the domain of this function. If you were to graph it, these are always easy to see with a graph, so you can kind of make use of a graphing calculator. But if I were to graph this function right here, this is what it would look like. And you can see basically everything from to the right of 1 is a continuous function. So it's just kind of a good way to validate the answer by looking at the graph. And that's it for part 2.